Fine, then we will continue with the definition of arithmetic branching programs. So we have identified size of ABP. So this is just size of the graph, and how many variables you have. And it depends on your on what you are interested in, but if you want, you can also include the constant bit size. Since linear polynomials on the edges from layer I to layer I plus 1, they have constants. So how big these constants are, if you want to measure, if you want to take that into account, then you can also include that in the size. Otherwise, usually it's only the graph size and includes the number of variables. Width is then the number of vertices in a layer, and depth is number of layers. Okay, and you can think of it as going from left to right. So let us see an example. So you have source here. So this will be width 2. So S to T. So the direction is left to right, and on this you have x1 plus x2. Here you have minus x3, x2, minus 1, x1, x1, and when I don't say anything, then it is assumed to be 1. Okay, the edge label is 1. So what is, so I will not draw the directions always. This is just going like left to right. So at T, what is the polynomial that you have computed? Just x2, x3, right? So you are, this ABP computes the monomial x2, x3. So the reason is that right. So there are 3 paths from S to T. So the first path is this, and second path is then this, and third path is this. Right, so there are these 3 paths. The first 2, whatever they compute, yeah, it's negative each other. So in the sum, it will not contribute. So the only thing that contributes is minus x3 times x2 times minus 1, which is x2, x3. So that is the model. So this has width 2 and depth is, so the longest path is length 3, so depth is 3. Size, you can see, just count the number of edges, vertices, and how many variables there are. So the sum will give you. Okay, now this pictorial representation is fine, but to analyze it, we also need a more algebraic representation, and that ABP has. So circuits, we don't have an alternative representation, but for ABP we actually have. Oh, so can you see that this ABP is also a circuit, because you can, instead of these vertices, you can think of yeah, but no, it is not so easy, because the number of paths can be exponential. So how will you implement that in a circuit? So I should leave it as an open question at this point. Is this a circuit? Is there a small circuit for this? No, it's not obvious because the sum is big. The sum is over all the paths. So at this point actually it is not even obvious whether circuits, this can be implemented by a small circuit. So for all you know, ABP may be a incomparable model, but it will not be, because we will now analyze it algebraically and we will give an alternate representation. So we can also represent this F by using adjacency matrices for the levels. Say of the level transitions. Okay, so from level I to I plus 1, look at this as a bipartite graph. There is an adjacency matrix. So for level I there is an adjacency matrix, and what is happening, what is the operation on these adjacency matrices that could correspond to the computation, ABP computation? Can you guess it? So it is matrix multiplication. So you can, so level 0 to level 1 you have this matrix, yeah, so let's say 0 1 0 or 1 1 1 2, so that's a row. Then level next level, let's say 2 to 3, so maybe I'll label them. So level 1 2 3 4. So now 2 to 3, the matrix is a square matrix. So you get x1 x1 and 0 x2, and finally it is a column vector 1 minus, and you can see that this evaluates to the same f, you get x2 x3. So this is happening because summing over all the paths from S to some vertex, that is being simulated by iterated matrix multiplication. Is that clear? And the first row looks like a polynomial, I mean it has polynomial entries, but we can further simplify it like this. Okay, so now this is the part where you are multiplying matrices that have polynomial entries, and on the left you have a constant row vector, on the right you have a constant column vector. So ultimately it will be computing a polynomial over the field. So this part, the central part, is called iterated matrix multiplication. And these matrices have linear polynomials as entries.
Plus 1, you look, so a column of the matrices, for one column is for one node.
Yeah, so you look at this, yeah, you will be looking at only this subgraph. So inside this subgraph, you see a bipartite graph and the adjacency matrix for that. Okay, that is the x1, x1, 0, x2. So you do this for every level and then multiply them. Okay, so that exactly simulates paths. And then, so when you multiply by these row and column vectors, you you actually get a polynomial. Intermediate computations are actually matrices having polynomial entries, and the matrices have dimension same as width. So these are width by width matrices, and intermediate will be width by width matrix with polynomial entries, but in the end you will get a single polynomial. But this iterated matrix multiplication is a problem in itself. So this is why you should focus more on this. These constant column and row vectors are not very important. So now can you see that this can be subsumed or this can be implemented on a small circuit? Because you simply have to multiply matrices, and matrix multiplication you can do by addition multiplication gates, right? So at any point of time there will be a W cross W matrix whose circuits you would know. Say you have two matrices, each of W cross W entries, whose circuits you know, and when you want to compute the matrix product, that is given by the obvious formula. So that will again be a circuit, and the growth in the circuit for this multiplication is only additive. And is this a formula? It isn't a formula, right? Because you are using an entry many times. You are using an entry around W square many times. And if you don't use that many times, then you will have to recompute that. So you'll have to make copies of that. So that in every multiplication it will blow up the formula size. So it is not a formula. I mean, it is not a small formula, but it is a small circuit. So that is a non-trivial thing. It was not obvious from the picture, but this representation immediately gives you that. So ABPs have small circuits. But may not have formulas, may not be true for formulas. Yeah, sorry.
So this width may change level.
Yes, the width from I to I plus 1 may be different. So then you don't get a square matrix. That is fine. This path interpretation only needs matrix multiplication to be defined, which it will be defined, because when you look at I, you are looking at I plus 1, and when you look at I plus 1, you are looking at I plus 1 cross I plus 2. So the matrix multiplication is always defined. It's unconditional on the dimensions. And the biggest matrix that you will need is the width. So that's it, or the biggest dimension that you will need for any matrix. So let us define this second problem or second model. So this I will shorten to IMM, iterated matrix multiplication. So IMM polynomial, we will call it, we will denote it by IMM n comma d. So this is the, let us just look at one entry of the matrix products, that is the top left corner entry, 1 comma 1th entry of the product. Of D matrices. where these are symbolic matrices. N cross N, let us say, symbolic matrix. Okay, so we have defined the polynomial IMM n comma d, and it is just a product of d n cross n totally symbolic matrices, which means that every entry is a distinct variable, a fresh variable. Okay, so how many variables are there? Well, d times n square. So there are d times n square variables in this polynomial, and it's a huge polynomial with variable d and n. The polynomial actually has a lot of monomials, exponentially many, but it has a very small ABP and it has a very small circuit. Okay, so it's an important polynomial. So symbolic would mean that each entry is a constant or a variable. Okay, so variables may also overlap. Each entry is a variable or a constant in the base field F. Okay. Yeah, any questions about this? So then we can write down this theorem based on the observations that if F has a width W, depth D, ABP, then F has an iterated matrix multiplication representation of size. So size of IMM is just the entries you see, the space required to describe these entries. This will be, yeah, so you have d many layers, so it is d times something. So what do you want to put here? D times what? So in a single matrix, what will be the, sorry?
W cube.
No, in a matrix there are W square entries. But remember, in IMM we have said that each entry should be a variable. It cannot be x1 plus x2. So what do you do with this x1 plus x2, for example, which was here? What do you do with this? Or which is actually the source of this is this. You have this x1 plus x2, right? So how do you implement this or replace this ABP, transform this ABP so that such things are not present, only variables are present or constants are present? You just increase the size of it by where you compute x1 plus x2 by a small ABP, right? You add a layer here. So if one path will, one subpath will compute x1, another subpath will compute x2. So you will add these edges, and so basically this particular edge where x1 plus x2 is, you will actually duplicate it, one with x1, the other with x2, and that will grow the width by 1. So you will have width 3 now. But the advantage is that now in the matrices you will have only variables or constants. So that will be an IMM representation. So this width basically grows by multiple of n, right? So Wn, and then you are squaring it. So you get Wn square. So it's just this simple transformation. So any width W, depth D, ABP also has an IMM representation. So matrix product, matrix multiplication of size D times Wn square. The matrices are Wn cross Wn. That's it. So this is Wn. What was the notation? Oh, number of variables. Okay, I don't. N was the width and depth. Okay, so width is Wn, depth is d. So this is IMM Wn comma d representation. So ABP can be converted to an IMM and IMM can be converted to an ABP. So if F has an IMM width comma depth, then it has the ABP will have width W and depth d ABP. Right, this is even simpler because just from the matrices you can read off the graph, bipartite graph that it represents. So the first thing is just convert linear polynomials on edges to an ABP with only variables. Or constants. That will give you an ABP of suitable dimensions. And second is that IMM to ABP, you just draw an ABP with layer I to I plus 1 described by the adjacency matrix. By the respective adjacency matrix. Okay, that is those are the ideas in these two. So you can see that ABP and IMM are equivalent models. Okay, and both of them can be. So since ABP and IMM are equivalent, and IMM can be implemented as a circuit, ABP is also implementable as a circuit. But they seem stronger than formulas. So that we can leave as an open question, let's say. So what's open is ABP cannot be written as poly S size formula. Okay, so the conjecture is that ABPs are stronger than formulas, and so ABPs, polynomials that are computable by ABPs in a small way, they may not be representable as small formulas. Formula complexity can be much higher than poly. Okay, this is an open question. What else can you compute with an ABP? So you have seen that you can compute matrix products, but what are the other examples? Yes, determinant will be a big example, but there is a even simpler example. So if you have a sparse polynomial, so a polynomial that has few monomials. So any polynomial f in n variables, constants f, constants in the field f, that has sparsity S. What is sparsity?
Number of times.
Number of monomials on which the polynomial is supported, or an upper bound on that. So, if the sparsity is less than equal to S, if there are less than equal to S monomials in F, and say it has degree D, so any polynomial of this type has a small ABP, has an ABP of size, what do you think, in terms of S and D and N?
With each path can compute a monomial,
Right.
and that would have degree D. So the max
Yes.
pathless you would require is D, and width is S.
Right. Right. So size is SD, and correct. Yeah. So the proof of this is that if you look at, so you prove this monomial by monomial. So for a single monomial, when sparsity is 1, then you just have to draw a line, a path which is a line, and which is just multiplying the respective variables. So that has size D, and then for S monomials you just have to repeat these many lines, and the sum of this is your polynomial. Okay, so sparsity gives you the size. That's a simple ABP construction. The proof is just by build the ABP for each monomial. Sorry?
This is also considered.
Well, for S equal to 1 it is tight. Okay. So it's an optimal bound.
Well, for S equal to 2, if you have so many variables, you can make it disjoint. Let's say D is n by 2 or something, and then this would be tight, right?
Yeah, so maybe I should not claim anything about that, because those things will need more proofs. But you can, the feeling is that this will be tight, and for S equal to 1 it is. If you have several monomials, then it will need a proof.
But if you have like disjoint monomial, variable disjoint monomial,
Sure, if you have variable disjoint, yes.
then you have to make it tight.
Yes, right. But for any polynomial,
Yes, of course.
okay. Any other questions? So the thing that we are now interested in is, what about determinant? EBP complexity of determinant. So we know that that determinant has a small circuit, but that doesn't mean that it has a small ABP, because ABP is a more restricted model. So what we will prove at the end of this chapter is that not only are determinants computable as ABPs, ABPs are also computable by determinants. Okay, so this will be, these two will be equivalent models, which is a very powerful connection. And this again is hard to conjecture, and more importantly, it is telling you something about something as fundamental in theory and practice as determinant. Okay, so we'll see that actually this connection will improve our results of determinant that we saw in the last class. So we got some parameters; those parameters will get optimized with this connection. So let us define symbolic determinant. So symbolic determinant d on some variables is a polynomial that equals determinant of an M cross M matrix with entries either they are field constants or they are variables. So that's a symbolic determinant, and the size of symbolic determinant is M. So yeah, this is nothing surprising or important. It is just we are just formalizing the determinant as a computational model. So we will say that a polynomial f has determinant complexity or determinant size m if that polynomial can be written as the determinant of a matrix m by a matrix with entries literals, which is variables or field constants. Okay, so just like we have circuit complexity, ABP complexity, there is also a determinant complexity of a polynomial, and symbolic determinant is exactly this, where the entries are literals. So the determinant is a polynomial. So the connection is with this model. These two models are equivalent. So next big connection is between the computational model, algebraic computational model ABP and symbolic determinant. So we will show that they are equivalent up to polynomial size.
So, when we are trying to do this between ABP and symbolic determinant, can this be done like inductively? So at each layer I, you compute all the.
That's a matrix. There is no polynomial. There is no single polynomial.
No, yeah, that's a matrix. But at each layer, if you then made a sink at that layer, then what you would have computed
Right.
would be that.
So you will get a matrix of determinants, and then you have to show that this matrix of determinant and another matrix of determinants, when you multiply them, that can be expressed as a single determinant without size blow up. So it is a pretty non-trivial connection. It will need combinatorial and especially graph theoretic interpretation of determinant. So we will need, because ABP, I mean you can guess this because ABP was defined as a graph, and so we'll have to see determinant in graph form and then connect the two, connect with ABP. So we'll need a graph interpretation of symbolic determinant. So have you seen this? How do you view determinant polynomial or determinant function as so determinant of a matrix you want to compute. That matrix defines a graph whose adjacency matrix it is. So what is the connection between determinant and that graph?
So it's a matching polynomial.
Yeah, matching is more to do with permanent. Thankfully, it has nothing to do with determinant. Otherwise, determinant would also be hard. But yeah, so we will we'll look at the definition of, so in the definition of determinant, every monomial corresponds to a permutation. So we will actually think of the permutation in terms of cycles in the graph, and we'll call it a cycle cover, and then we will say that determinant is computing signed cycle covers. So basically it is a sum of the weights of cycle covers over all cycle covers. So we'll do it slowly. So let us first make permutation graph friendly. So any permutation on elements 1 to n can be decomposed into cycles, cyclic permutations, right? So instead of showing this for a general permutation, let us just see an example, because that is enough to understand. So suppose you send 1, 2, 3, 4, 5 to so this is, let's say, ordered. So this you are sending, okay, let me make it ordered. 2, 1, 3, 2, 5, 4. Okay, so 1 is mapped to 1, 2 to 3, 3 to 2, and so on. So what is the cyclic decomposition of this permutation? So 1 is fixed, right? Right. So 2, 3, 3, 2, that's a cycle. So we'll write it compactly this way, and the other cycle is 4, 5. So these are cycles of length 2, and this has I mean, we are not writing 1 here. So 1 also you can see as a cycle, which is basically a self loop. So there are 3 cycles. Okay, there is 1 cycle of length 1 and 2 cycles of length 2. So that is one thing. The other thing is we can associate a sign with this. So with sign, we want to associate with every permutation plus or minus 1. So what do you think it will be?
Number of flips. Or even flips.
Yeah, so flip is done by this kind of a even cycle. Flip as in swap. For example, it is done by 2, 3, and that in general, if it's an even cycle, we'll call even cycle, we'll give it sign minus 1, and odd cycles we will give sign plus 1, and then we will just multiply the signs. So here so basically it will be minus 1 to the number of even cycles. So which in this case would come out to be minus 1 square, 1. Okay, so we have defined 2 things: cycle decomposition and the sign of a permutation. So to compute the sign of a permutation, you compute the cycle decomposition. Now convince yourself that it is unique. There is only one cycle decomposition, and well, it is unique mainly because of the disjoint nature of this. 2, 3, and 4, 5 are disjoint, right? So you can easily show that the cycle decomposition is actually unique, and then look at the number of even component cycles and parity of that. So you may have written these programs in ESC 101, for example, where you compute the number of inversions, and so that is related to this. This even permutation, odd permutation, I think has multiple definitions, but they are all equivalent to this, what we just did. and so this will now be the also the sign that appears in determinant. So another, based on this, we will define in a graph G a cycle cover. So this is a partition of vertices Vg into cycles, where we will be assuming that the cycles are disjoint and simple. So cycle cover of a graph is basically what it says, that you try to cover your graph by cycles that are disjoint, and within a cycle a vertex doesn't repeat. Okay, so it's a simple cycle. Every cycle is a simple, and then they are disjoint and they cover all the vertices. Okay, that's a cycle cover in a graph. And so by the above connection, you can see that cycle cover is basically a permutation as well on the vertices. It can be thought of like that, and it has an associated sign. So this is now the place where you can see the connection between determinant and the underlying graph. So what a determinant computes of a graph. Any questions about the definition? Okay, so then let me just write down the connection as a theorem statement. So here we will say that if G is a graph, on vertices, let's say 1 to n, set 1 to n, with adjacency matrix given to you, n by n matrix with entries xij n cross n matrix. So that's the adjacency matrix, and this is the underlying graph. So then what is the determinant of x? So determinant of x equals, go over all the cycle covers of G, and for each cycle cover take the sign and the weight and sum it up. That will be determinant. So where sign of C is defined as before, and weight of C is just the, what is weight of a cycle cover? What is weight of a cycle first?
Product of all.
Right, so weight of a cycle is product of the edge labels or weights, and then weight of a cycle cover is all the cycles, product multiply the weights. So whatever edge E you see in the cycle cover, weight of that and product. So maybe WT here also. Weight of E. Okay. So what is the proof of this? I think it should be clear by the previous example of permutation decompose it into cycles. By that example, you just have to use that example on the definition of determinant. So determinant by definition is going over all the permutations. Now, this thing is so I want to write this as weight of C, weight of some cycle cover. Want to associate those two to consider the cycle decomposition of sigma. So cycle decomposition, let's say, sorry, so cycle decomposition of sigma gives a cycle cover of the graph. So call it C. Okay, is this clear? When you decompose sigma, basically will decompose into these cycles as you got before 2, 3 and 4, 5. So you get, and 1 is the self loop. So you get these 3 cycles. So similarly, this C, any C would give you a bunch of disjoint simple cycles in the graph G. And now you will look at the weight of that. So weight of this C is what? So the weight on I sigma I is x I comma sigma I, right? This is what is happening inside the graph. So graph is G, and inside this what is happening is if sigma maps I to sigma I, then the weight is this. So when you look at a cycle, inside C, then you can see that weight of this cycle is exactly the product of these x I sigma i's for I appearing in the cycle, and then hence also across the other disjoint cycles. So weight of C is exactly equal to the product xi sigma I, and since product is obviously commutative, so commutativity of the product is used, you will get all the things from I1 to In. Okay, you can write in this order, but they will be clustered according to cycles in this proof, and then you reorder them because multiplication commutes obviously. Yeah, so maybe this it's important to state here that this determinant is the usual determinant. So it is in this polynomial ring. Okay, so this polynomial ring, it is by definition commutative. So you will get this property immediately. And second thing is sine of C. So if you recall the definition of sine of sigma, you will see that it's the same. There is really only one definition for the sine of permutations. So with this, the proof is complete. Okay, maybe one more thing. So for every sigma, there is a cycle cover. That is clear. What about the converse? For every cycle cover, is there a permutation? So every cycle cover C of G uniquely specifies a permutation. On n elements. Right, this is again this follows from the disjointness of these cycles and their simplicity also. The ones that are self loops, they will be dropped. because they are not being transformed, they are not being moved. The ones that are being moved, they are within a cycle, but the cycles across are disjoint. So this is clearly a permutation. So that finishes the proof. Okay, so we get, I mean, this sum over cycle covers gives you all the permutations. So basically, there is a bijection between cycle covers and permutations. There is a bijection, and under this bijection, the weight of C and weight of sigma, or weight of C and the monomial, they are the same. Okay, so that means that determinant is exactly this, that the two sums are the same. Is that clear? Okay. Yeah, but it doesn't seem that we have done something great, because there is a bijection. So either of these things are hard or easy for the same reason. It doesn't tell us anything particularly new. But at some point it will. At some point it will give you a big result. We'll use this. Okay, before that, as a corollary, you can also say something about the permanent. So permanent of n by n matrices also is related to the cycle cover. So drop the sign. So if you just took the sum over weights of all cycle covers in the graph, underlying graph, then you will get permanent. This, if you specialize to a bipartite graph, then you will get matchings.
Slightly different, right? Because in the bipartite graph, you take the representation is different, right?
The representation is different, yes.
Incidence or no?
Well, it's
I don't know. Where on one side
part
you have,
of
no, it's not, because on one
It is the original matrix.
It's one part. If you draw
Okay.
full matrix,
It's
one
one
is
is
this is
symmetric.
0 and one is
Yeah.
symmetric. So you just take a part.
It is a part, yeah, right. So yeah, you have 2n, yes, you have 2n vertices in a bipartite graph, assuming yeah n and n, but you don't look at 2n cross 2n matrix. You just look at n cross n. So you just look at the part that already contains all the information. Yeah, so for that, yes, exactly. So specializing X to that, you will get the correspondence with matchings, which is also naturally related to cycle covers. Okay, so now let us do one part of the model equivalence, which is, so what do you think will be easy, reducing ABP to determinant or determinant to ABP? Determinant to ABP will be easy.
No, ABP because
Right, so determinant to ABP will actually be the hard part. That came out as a surprise in the 80s. It's a result by Mahajan Vinay. So that we will do later. That's the hard part, because it really, I mean, even if you are interested in practical algorithms, it was a new thing, because if you recall, Gaussian elimination will require division. So say you want to compute determinant in a ring, entries are in a ring which doesn't have division. So it is not a field, for example. So in such a ring, since you cannot divide, you cannot use Gaussian elimination, and then you cannot even compute determinant in practice. Okay, and there are many conceivable simple rings where this problem will appear, and then there is actually no algorithm except the trivial exponential time algorithm to be implemented in practice. So Mahajan Vinay's result will actually give an ABP for determinant, which in particular would mean that no division is required. Determinant is a polynomial. Why should you require division? So ABP representation, once you get, well, you will just do addition multiplication. There is no division and can be efficiently implemented. Okay, so that will be a really new thing about, or even for the practical implementation of determinant. So that is the harder thing. Easier thing now would be with the cycle cover interpretation. Easier thing would be to actually see ABP as a determinant, because ABP is defined as a graph with sum over paths. So if you can make those paths into a cycle, then it will be like summing over all the cycles, and that can be written as a determinant. Also the signs should also match. So you want to convert ABP picture, given up ABP picture, you want to convert it into a, it will be a small modification, it is not hard. You simply convert it into another graph where you have added some reverse edges, so that these paths make a cycle. Say all the cycles have the same length, so the signs will be the same, and then the adjacency matrix of this graph will have determinant equal to ABP. Okay, so it will be as simple as that. It's just working with the graph representation. So let's do that.
If we add reverse edges, are we keeping true to the definition of the ABP?
No, not certainly. No, certainly not. No, we are keeping true with the definition of determinant. ABP remains what it was. Determinant will be of something else.
Sign or negative, yeah.
You're not writing a, okay, so you're not writing ABP as
No. That is not the question. The question is to write ABP as a determinant.
Can we follow a similar approach to get towards permanent as well, like getting rid of signs? And what would be the difficulty in face of
Yes. Let us see what is the difficulty. No, but so then what would you show? You would show that ABP reduces to permanent. Nobody is surprised with that.
Right.
It's trivial.
The surprising fact would be to convert to half per ABP.
Exactly. So again, the hard part, whether permanent can be written as an ABP, that will shock many people to death. But this one will not, because permanent is actually complete for VNP. So everything permanent can compute. So if F has width W, depth T, ABP, then there is a determinant. Then it has WDN size determinant. Yeah, I'm not sure why we are multiplying everything, but we'll see in the proof. So the graph we will get will probably have WDN vertices. Right. Okay. Yes. So to right. So you first look at the IAM where the width becomes a WN, and so there are D layers, each with the WN vertices. So you get the product of everything. That is the number of vertices in your graph. So the adjacency matrix will have that as dimension. That is your determinantal complexity. Prove this. It's the last lemma today. So firstly, make the ABP edge weights. Literal or literals, that is in F union X bar. So that makes the width WN. So that is not very important. So once you are in this situation, right, width grows but the depth does not grow. So depth remains the same as before. This is important, yeah. So width changes but depth doesn't change, and so now look at this picture, this graph, and let us add the edges. So let G be the directed underlying this AVP. So modify it to a graph G prime as follows. So what we will do is add a unit weight, which is weight equal to 1. Let me write weight equal to 1. So add a weight equal to 1 edge from T to S. Okay, so sync to source we add a reverse edge. So a path becomes now a cycle, S to T and back. But you would be interested in a cycle cover, right? So what will you do with the vertices that have not been used? Exactly. So that's the other thing. So on all other vertices, so yeah, currently we have only added one reverse edge from T to S, and all the other vertices, internal vertices, add self loops. Of again weight 1. So this now it should be now obvious that in the G prime, whenever you look at a cycle cover, or okay, let us start with the easy case. So in G, if you look at a path from S to T, that corresponds to a cycle cover in G prime, because take that path to S to T, come back, and on the other vertices that have not yet been used, use the self loops. So that is a cycle cover of G prime. Now conversely, what is a cycle cover of G prime?
And that is exactly remove self loops.
Right. So other than the self loops, the only way to get a cycle is to use this newly added reverse edge. But if you, as soon as you use the reverse edge, it means that some path from S to T is being utilized. So every cycle cover in G prime corresponds to a path in G and converse. So it's a bijection. So C in cycle cover of G prime uniquely specifies a path S to T in G. Moreover, okay, let's talk about the signs, right? Also, weight is clearly not changed because we have only added unit. New weights are unit weights, but the sign.
You can just make the T to S edge plus or minus 1, right, depending on the depth.
Right, so you would need no, I think you would need the, okay, so thing to observe is that what is the length of a path from S to T? Does it change over paths? It's the same, right? It's equal to depth. So all the paths are of the same length, which means once you look at the cycle given by this path, the remaining vertices, their number is always the same. So all the cycles have the same cycle covers have the same sign, of the same sign. That is it. So the signs are the same. You can assume it to be +1 because, as Abhibhav is saying, you can just, the reverse edge, you can choose the appropriate thing, +1 -1. So you can assume that it is 1 without loss of generality. Is that clear? And right, and the converse is also true. Every path in G uniquely specifies a cycle cover of the same sign in G prime. So this sets up the bijection, and this, then the two things imply that determinant of A prime, which is the adjacency matrix of G prime, this is the same as the determinant of A. So the adjacency matrix of G, right? And finally, you can do the size calculation. So you also get that A prime number of vertices in G prime is just Wn cross D. So that's the determinantal complexity of the original ABP. That finishes the proof. Is this clear? Okay, so yeah, that was the easy part, although it is still surprising because syntactically it doesn't make any sense. So you were looking at matrix multiplication, iterated matrix multiplication, and now we have written it as a single determinant, right? So syntactically it seemed impossible actually, but semantically there is this graph connection interpretation that makes them the same. So iterated matrix multiplication and determinant are essentially the same up to this poly growth in size. So more surprising property would be the converse. So this is a result by Mahajan and Vinay. Well, not 80s, it's actually 97. That determinant on n by n matrices, it has an ABP which is pretty small. So the width is only n square and depth is only n. Over any commutative ring. So in particular over fields it is true, and the new thing that happened, even in terms of even as an algorithmic phenomena, the new thing is that when you are working over a commutative ring where you cannot divide, still, so you cannot use Gaussian elimination, which was the only known way to compute determinant, because the previous algorithm which you saw, this circuit based thing, right? Will that work over non-fields?
No, because a multiple of the powering sum is equal to, I mean, in reconciliation you're scaling up the powering sum by a multiple. So in the end you'll have to divide by those 1, 2 all the way to
But
k.
right. Yeah, but that is still manageable.
It's not actual division.
No, it is division, but then that is only a question about the characteristic of the ring. So if the characteristic is large, then you could have done that. Yeah, but I have to think about it whether.
How will it work if one of those elements, say over here Z6 or something?
No, sure, but assume that the characteristic is 0, for example. It's a commutative ring with characteristic 0.
Without 0 divisors? Yeah, okay.
And it has 0 divisors.
If it, oh, but the characteristic is 0, then it's fine. Okay.
Right.
So divided by constant.
Right. So I guess that is another way. So then this is more. I mean, this optimizes even that, because the width here is only n square, and depth is exactly is order n. So you have around n cube sized ABP representation. So when you convert it into a circuit, you will actually get a lower depth. We will see that. So yeah, maybe we'll do it next time. So we'll prove this. Any questions? Okay, so then we will meet next week, Tuesday. I'll also release the first assignment this week. Every month we'll have one assignment, I think. Okay.